So, which methods of glycerophospholipid synthesis can bacteria or prokaryotes use? Well, there were two methods, 1 and 2, but bacteria, prokaryotes, can only use method 1. You cannot use method 2. And method 1 basically started with the CDP-DAG, or the activated diacylglycerol, which I've drawn here. The activated diacylglycerol. I've drawn it in a slightly different way here, with the CDP portion sort of extending out to the right as opposed to down. That might be a little bit easier to see. Now, how did we get this? We mentioned that we started with phosphatidate and we added to it a CTP, and then a pyrophosphate came off to give us the CDP-DAG. So what exactly is happening here? Well, phosphatidate already has this phosphate group, and we're adding this purple portion here that's coming from CTP. CTP has 3 phosphates. 2 of the phosphates come off as a pyrophosphate, so there's only 1 phosphate group left on that, and that basically means that we're adding a CMP portion to the existing phosphatidate. Now, what you'll notice is that the name doesn't seem to imply that, right? It says CDP-DAG. So it sort of can get confusing because it might make you think that this entire, like both of these phosphates came from CTP when they didn't. One of them was already there from phosphate, or excuse me, one of the phosphates was already there from phosphatidate, the red one, and then the purple one came from the CTP. So we're effectively adding a CMP, but the name should still make sense because it kind of looks like a CDP attached to a diacylglycerol. So just for the naming's sake, it makes sense, but the name alone could be confusing in allowing you to understand which parts of this molecule are coming from what. Anyway, prokaryotes need to start with this activated DAG in order to make glycerophospholipids. Okay, so we mentioned that glycerophospholipids are made in 4 steps. The first one is making the backbone, the second one is adding the acyl groups. And to make phosphatidate, that's basically the first 2 steps, and we saw that already. So, especially when we talked about triglyceride synthesis. So, up until phosphatidate, we've basically done steps 1 and 2. So step 3 is adding the polar head groups, and in order to do that, we have to activate the DAG first, at least in prokaryotes. So let's add these groups. So to the left here, you'll see that I'm adding this amino acid. This amino acid is serine, and we're specifically have to add it as an alcohol, right? This is the alcohol that we're adding, right? This is the polar head group alcohol that we're adding here. Let's see if I can label this in a, let's do orange. Actually, let's do yellow. No, let's do pink. This is the polar head group alcohol that we're adding here. So the alcohol specifically that's going to be connected is right there, the OH group on the serine. So what's going to happen is that that part is going to be attached. That's going to actually attack the phosphate, the red phosphate group of phosphatidate in the CDP-DAG. So this OH is going to be connected, or this O from this OH is going to be connected to this P to give us this molecule here. And so this basically replaces the CMP portion. So the CMP will actually fall off. So the CMP portion falls off, and it's replaced by this serine, and so we get this. Okay. And it might even be a little bit more helpful to kind of see this O here drawn in this pink color to show that that O, this is the OH that's connected. Okay, so that gives us phosphatidylserine, which is basically a glycerophospholipid. That the enzyme that catalyzes this step is called phosphatidylserine synthase, okay, which makes sense. It's making phosphatidylserine. Now, that is basically step 3, right? If we think about the process by which we do this, this is step 3. We're adding this alcohol head group to make a glycerophospholipid, and then we're basically done, right? However, what can follow is step 4, which could include modifications. So we can go from phosphatidylserine to phosphatidylethynolamine. And if you notice the difference between these two molecules, it's at the head group. The only portion that's different is right here. This carboxyl group is gone, right? So phosphatidylserine was decarboxylated, and it lost that carbon dioxide to give phosphatidylethynylamine, and that step was catalyzed by phosphatidylserine decarboxylase. That makes sense. It's acting on phosphatidylserine and removing a carboxyl group to give phosphatidylethynylamine. So that would be basically the step 4, right? The modification of an existing glycerophospholipid to give you the final product. Okay. Another case could be replacing the CMP portion on the CDP-DAG with a different alcohol, say glycerol 3-phosphate. And in glycerol 3-phosphate, this might be helpful to sort of track these carbons. If we number these carbons 1, let's do it in orange. If we number them as 1, 2, and 3 here, which OH group is actually going to be the OH group that attaches to the red phosphate in the CDP-DAG? Well, it's going to be the OH group on carbon number 1. Why is that? Well, first of all, we can see that here in this, because this portion here that was added, the phosphate group is on carbon number 3, so this is carbon number 3, this is 2, and this is 1. That should be pretty clear from looking at the molecule. But it should also make sense why this OH in particular attacked. It's the least hindered, and it's away from this negative charge. This negative charge and the negative charge on this oxygen definitely want to stay away from each other, which makes sense in the product while they're so far away. And this OH here is on the end of this molecule, whereas this OH is kind of on the carbon number 2, is kind of in the middle of the molecule. So carbon number 1 gets connected to the O over there, and or to that phosphate group there. And now we have phosphatidylglycerol 3-phosphate. So this is a glycerophospholipid, and again, we're talking about another step 3 here. And this one is catalyzed by phosphatidylglycerol 3-phosphate synthase. Again, that's just the name of the thing that we're making, followed by synthase. So now that we have that, we can modify it to give us a different product, to find another product. And basically what we're doing here, going from phosphatidylglycerol 3-phosphate to phosphatidylglycerol, is that we're removing this terminal phosphate out here. We're getting rid of this. So how do we get rid of that? Well, we add phosphatidylglycerol 3-phosphate phosphatase, which removes phosphates by hydrolyzing them off. So we'll have H2O, and that'll kick off the phosphate. And we're left with phosphatidylglycerol. Right, so that was a modification that gave us this. It can be modified even further. In fact, we can add another phosphatidylglycerol, which I've drawn here. Now notice this in purple here is pretty much identical to this one that's color-coded a little bit differently. It's got these two acyl groups up here. It's got that, and then it has the phosphate with this glycerol portion out here. Okay, so these molecules are identical in their overall sort of schematic, and we're going to connect them. Okay, and when we connect them, this purple portion of glycerol is actually going to fall off. Okay, so I'm just going to write glycerol here to indicate that this portion here will fall off. Now, I'm going to draw this one up here a little bit differently. We numbered these carbons as 1, in orange, as 1, 2, and 3 earlier. Let me just go back and show you that we did that. So down here I'm going to show it a little bit differently. So those 3 carbons, 1, 2, 3, instead of drawing them out to the right like that, I'm going to draw them just down like this. 1, 2, 3, to show that the phosphate from this phosphatidylglycerol that's coming in, it's adding to this third one, this third carbon, and that phosphate is connected to number 3 on this glycerol. So if I call this 3', 2', and 1', just to indicate that they're different, this carbon here is going to be 3', this is going to be 2', and 1', and that should make sense because it might be confusing just looking at this at first and seeing that the R3 is on top, R4 is on the bottom, and then in the product where we get this molecule called cardiolipin, R4 is above R3. That might be confusing to people, but it's only confusing if you don't pay attention to the numbering pattern of this actual molecule and realize where the connection is being made. But once you see that, it shouldn't be too difficult to see. Now this molecule, cardiolipin, is made by the connecting of these two phosphatidylglycerols, at least in bacteria, by an enzyme, cardiolipin synthase, specifically the bacterial version. And this molecule, cardiolipin, is an important component in the inner mitochondrial membrane, as well as bacterial membranes, and it's also clinically significant because of its presence in bacterial membranes. I'm not going to really discuss any of those details now. I just figured I'd draw it because it came up as something that is clinically significant. So I hope that video was helpful in discussing how glycerophospholipids are made in prokaryotes. Next up is eukaryotes. Thank you for watching.